In this lesson, we're going to talk about angles and how to find them. Specifically, we're going to talk about something called a principal angle and a related acute angle, and we're going to have to find those in different situations. The other thing we're going to look at in this lesson is how to find exact trig ratios for special angles, 30 degrees, 45, and 60 degrees. And we're looking for an exact trig ratio, so we're not going to be using your calculator, but we're going to be deriving the exact ratios. So to begin this lesson, we need to all understand certain terminology. So the terminology in particular we need to look at is what a principal angle is and what a related acute angle is. So up until now, we've been dealing with angles in a triangle. So we might have a triangle like this, and maybe this is a right angle, and we're taking a look at this angle right here. So what we're going to do is we're going to take this triangle right here and we're going to put it on an XY grid. So for example, if I were to draw a triangle on this grid, it would look something like this. Oops, there we go, something like this. So we're going to be measuring this angle right here, but we're going to measure it on the XY grid. And that's where we're always going to start measuring angles from. We're going to start it on the positive XY grid, and then it's going to open up from there. So let's talk about what a principal angle is. A principal angle is the angle between the initial arm and the terminal arm. So I said that all angles are going to start on the positive x-axis. So here's the initial arm, and this initial arm is opening up counterclockwise to whatever point we want to stop it at. So in this picture, it stops right here. So this angle in between here is called the principal angle. So the principal angle has to be between 0 and 360 degrees. So it can start here and then slowly open up. It can go all the way around until it hits 360. So that's the biggest principal angle that you could have. When we're trying to find a principal angle, we always measure from the initial arm and we go counterclockwise to the terminal arm because the angle has to be between 0 and 360. So we're measuring this angle here as opposed to this angle here. We could also measure this guy too. That's going to be its own angle. But if we measure from the initial arm here clockwise, so going around this way, that's going to give us a negative angle, and we're going to talk about that. So our standard position is we start on the initial arm here and we go counterclockwise. So this is going to be positive 90 degrees. This is maybe another 45 degrees. So maybe this is 135 degrees total. If we were to start in the initial arm here and go counterclockwise, it's no longer a principal angle, but we're allowed to do it. But we're going to measure these as negative degrees. So this would be negative 90 degrees. We're going to talk about this more a little bit later. But the most important thing to understand is what an angle looks like in standard position and what a principal angle is. Here's the initial arm. It's going to open up counterclockwise. So another really important term we're going to talk about is called the related acute angle. The best way to explain what a related acute angle is, it's the acute angle. Acute means it's less than 90 degrees. So this is not less than 90 degrees. This is over 90 degrees. That's called obtuse. But this guy here, that's acute. That's less than 90 degrees. So it's the acute angle between the terminal arm and the x-axis. So here's our terminal arm. Here is our x-axis. Here it is, right here. So this must be the related acute angle. If I had a angle maybe down here, or if I had a terminal arm down here, that was an awful line, but that's okay. Our related acute angle would be the acute angle between the terminal arm and the x-axis. So it would be right here. Another good way of understanding what a related acute angle is that it's the angle that would be in a right angle triangle. If we were to make a right angle triangle using this terminal arm, it's the angle that's inside of it. So if we can make a right angle triangle with the terminal arm by doing that. What we don't want to see happen is we're not making a right angle triangle with the y-axis. It's always, always, always with the x-axis. So I'm just going to underline this again. It is always with the x-axis. So if I were to make a right angle triangle with this terminal arm, this is our related acute angle. If I were to go and do an example on the other side here, so here's another terminal arm. If we made a right angle triangle with the x-axis. Here, this inside thing, this inside angle right there, that is a related acute angle. So we typically use theta to denote a principal angle and beta to represent a related acute angle. So some takeaways. Angles in standard positions start on the positive x-axis. If it opens up counterclockwise, the angle will be positive. So this is positive 90 degrees, positive 135 degrees, let's say, or 120. If it starts on the initial arm it starts on the positive x-axis and opens counterclockwise, then we know that this is going to be negative angle. So this is going to be negative 90, negative 180, for example. A principal angle has to be positive and is defined as between 0 and 360, okay? So this could be the principal angle of 120 degrees. As long as it's positive, it's between 0 and 360. The related acute angle is the acute angle when we between the terminal arm and the x-axis. Another way to think about it is if you were to draw a right angle triangle with that terminal arm, where we're dropping down an altitude from to the x-axis, it's whatever angle is in there. So again, it must be with the x-axis, nothing to do with the y-axis. So this question asks us to draw each angle and then label its related acute angle. So we're going to figure out what the principal or what the angle is and then label the related acute angle. So before we can do that, let's first start labeling just our XY grid when it comes to angles. So we know that we are going to start on our initial arm has to start on the positive x-axis. So let's call this 0 degrees. So this is 0 degrees, 0 degrees. If we were to open it up in the positive direction, we would go over here, and this would be 90 degrees. If we were to continue opening up 90 degrees, what would this be? Well, this would be 180 degrees. So this quadrant is 180 degrees. And then if we continue it again, one more, what's 180 degrees plus another 90 degrees? Well, that's going to be 270 degrees. And what if we were to open it from our initial arm around to here, around to here, around to here, and all the way back? Well, that would be 360 degrees. This gives 0 degrees. This also can be 360 degrees. So now this is going to be easier for us to draw 220 degrees. So now that we have labels on our XY grid, it's going to make it easier to figure out where 220 belongs. Mathematicians found that it's hard to just talk about which section of the grid we're talking about. So what they did is they came up with quadrant names. So this over here, this guy over here, is called quadrant number 1. So we call this quadrant 1. So I'm going to put a little 1 here. This quadrant is quadrant 2. The quadrant beneath it is called quadrant 3. And next to it is quadrant 4. So when we speak about each of these sections, we call them quadrants, and we have numbers for them. So clearly, when an angle opens up, it starts in quadrant 1, then goes to quadrant 2, then to 3, and then to 4. So now we have all the labels that we need to really answer this question very quickly. Where would 220 degrees be? Which quadrant? Well, it has to be between 180 and 270, so it has to be in quadrant number 3. So maybe it looks something like this. We can label 220 degrees now by starting on the initial arm and drawing an arrow all the way to the angle. So this is our principal angle. It's a principal angle because it's between 0 and 360 and it's starting in standard position, so starting right over here. So there's our principal angle, which is 220 degrees. So we're halfway there. The next question said, or the second part said, what is the related acute angle? Well, we have to figure out what the related acute angle is. Is it this guy here, this first one, or is it this guy here? Well, the related acute angle is the angle if we were to draw a right angle triangle with the x-axis. So it's this guy here. So I'm going to erase this one here because that's absolutely not correct. So we're looking for this angle right over here. This guy right there. So I'm going to label it. I'll use red. So this is our related acute angle. This is our B. We have to figure out what this B is. So we know what this whole angle is. This whole angle is 220 degrees. What else do we know? How can we figure out just this guy, this little slice right here? Well, don't we know that from here to here is 180 degrees? So the leftover of 220, if we take away 180, we must be left with our little beta value. So I can find beta by just taking 220 and taking away 180. And that's going to be 40 degrees. So this guy here must be 40 degrees. So that's our beta value. So our theta, which is our principal angle, is 220, and our beta is 40 degrees. Let's try drawing negative 110 degrees now. So because this is negative, we must know that, well, we know that we're starting on the positive x-axis, and we're going to go clockwise around the grid. So if we start here, this is going to be 0 degrees, just like before. So I'm going to write a little label that we know this is 0 degrees. If we're counting to negative angles, so if we go counterclockwise here, this isn't going to be 270 anymore. This is going to be 90 degrees in the negative direction. So this is now negative 90 degrees. And we're going to keep going. This is 90 degrees in the negative direction. This is 180 degrees in the negative direction. So this is negative 180 degrees. And if we keep going, this is negative 270 degrees. And if we go all the way around in the negative direction, this must also be negative 360 degrees. So knowing that, what quadrant is negative 110 in? Well, it has to be in this quadrant here because negative 110 is between negative 90 and negative 180. And that's quadrant 3. So this is our quadrant number 3. The quadrant numbers don't change whether we go clockwise or counterclockwise. That's still 1, this is still 2, this is 3, and this quadrant is still 4. So we must be in quadrant 3 again because it's negative 110 is between negative 180 and negative 90. So I'm just going to draw a line here. And be careful that this isn't negative 110. We started here and went clockwise. So this angle here, that's negative 110. That's negative 110 degrees. So is that a principal angle? Go back to the definition of what a principal angle is. A principal angle has to be between 0 and 360 degrees. And this is not. This is less than 0. So our principal angle has to be up here. This is where the principal angle is. So what does this angle measure? So if I want to know this guy here. What's this angle measure? Well, I know all the way around a circle is 360. And if I take away 110, whatever's left over must be our principal angle. So if I can find theta by just taking 360 and then just taking away 110 and seeing what's left over. And we know that that's just 250 degrees. So this is 250 degrees. So that must be what our principal angle is, 250 degrees. So 250 degrees and negative 110 degrees, they're called coterminal angles. They're angles that have the exact same terminal arm, but they have different angle measures. So these angles are both at the same time 250 degrees and negative 110 degrees. They look exactly the same. Okay, so with that said, let's just find our quick little beta. So our beta is our related acute angle, and that's going to be the angle between the terminal arm and the x-axis. So if we were to draw this right angle triangle, here it is. We're looking for this guy right in here, so that's our beta. So what is the measure of beta? Well, actually, this happens to be in the same quadrant again, so we're going to do it the same way, where we know this whole thing here is 250 degrees. And we know just from here to here is 180 degrees. So I got to figure out what's this extra little bit here. So if I take the whole 250 and I take away 180, what's going to be left over? So to find my beta, I'm going to take 250, take away 180, and you get 70 degrees. So that means my related acute angle must be equal to 70 degrees. Let's try one last weird example. This one says draw 390 degrees. Well, we know that that's bigger than 360. So what is this going to look like? Well, we're going to start on the positive x-axis. We know we are going to go to the left, so we're going to put up counterclockwise because it's positive. This is going to be 90 degrees. This is going to be 180 degrees. This is going to be 270 degrees. So let's draw a little arrow as we do this. So we're starting, this is 90 degrees, then we have 180 degrees and 270 degrees, then 360 degrees, And then we're not quite at 390 yet. We got to go 30 degrees more. So 390 is all the way around there. 390 degrees is going to look like this. So this terminal arm started here, opened up, wound around, winding, all the way past 360, 30 degrees more till about there. So this is 390 degrees. What's the principal angle? Can this be a principal angle? It's positive, but is it between 0 and 360? No, it's too big. So what would the principal angle be? It would be just from here to here. What is that angle measure right from there to there? And if you can figure it out in your head, it's just 30. So I know I know that all the way around from here to here is 360. How much extra do we need to go to make 390? Again, all the way around is 360. What's 390 take away 360? Well, it's going to be 30 degrees. This guy right here is just 30 degrees. And that, here we go. And that is our principal angle, our theta. Now let's find our beta, our related acute angle. So related acute angle is an acute angle between the terminal arm and the x-axis. So I'm going to draw an altitude down here to make a right angle triangle. So it's this angle right here. That is our beta. And in this case, it happens to be exactly the same as our theta value. It's 30 degrees. We already know that measure. So we're done. So try this last guy on your own. So here I want you to draw negative 330 degrees and figure out what the principal angle is and what the related acute angle is. Go for it. So if you press play again, hopefully you try this on your own. Which quadrant did you put it in? 1, 2, or 3? Hopefully you put it in quadrant number 1 because that's where it belongs. Because if we're dealing with negative degrees, we're going counterclockwise. This would be negative 90. We're going clockwise. This would be negative 90. This would be negative 180, negative 270. Negative 330 is between negative 270 and negative 360. So it has to be somewhere here. So if we were to draw it, it would look something like that. That is what negative 330 degrees is. That's obviously not a principal angle because it's not between 0 and 360. Here would be our principal angle. Our principal angle would be like this. That would be between 0 and 360 degrees. So our principal angle, what the heck does that have to be? Well, I know all the way around is 360. From here to here is 330. So what must this be? This is again just 30 degrees. So that's what our principal angle is. It's just 30 degrees. And again, our related acute angle is the exact same. Nice and easy. Our related acute angle has to be this one here. It's acute. It's the acute angle between the terminal arm and the x-axis. Done. Now that we understand the terminology of angles, we're going to move on to special angles and their ratios. So there's a few angles that we have exact ratios for sine, cos, and tan, and we have them memorized. And the angles are 30 degrees, 45 degrees, and 60 degrees. So sine, cos, and tan of angles, we've put them in our calculator now for 2 years. They can be really, really ugly decimals. But mathematicians found that these 3 angles in particular have really nice, easy to work with exact ratios for sine, cos, and tan. And that's really, really helpful to have exact ratios, especially when we're doing calculus. So it's expected that we memorize all the ratios of 30, 45, and 60, which means we need to know what the sine, cos, and tan of each of these 3 angles are. So it's easier to understand how to memorize these or what each of the ratios are if we actually derive them. So we're going to derive what the sine, cos, and tan is of each of these angles. We can put it into our calculator, of course, but I want the exact ratio for each of these, not a rounded number. So let's start with special triangle. Let's start with special triangle number 1, where the instruction says to begin with an equilateral triangle with side length 2. So let's just fill this in. If this is equilateral, each of these is 2. So we have 2, 2, and 2. Now it says split it in half to make two right angle triangles. So I'm going to split it in half and make two right angle triangles. So let's label this guy together. So just right underneath, what do I know about this right angle triangle? What do I know about this right angle triangle here? Well, I know that this hypotenuse is 2. Okay, so this is just like, it's like I cut this right angle triangle and I put it here. So I know this guy is 2. Do I know this guy? No, I don't know. It can't be 2. 2 is the hypotenuse. It has to be less than 2. We don't know this guy. But do I know this guy down here? Well, if this is an equilateral triangle, when I brought the altitude down, it would have exactly cut this in half. So this must be 1. So can we find this side length right here? Well, of course we can. We can find that side length just by using the Pythagorean theorem. So if we use the Pythagorean theorem, we have a squared. Let's call this a. So we have a squared plus b squared, which is 1. So 1 squared has to equal c squared, which is 2 squared. So I have a squared is equal to 4, take away 1. A squared is equal to 3. And so a is equal to the root of 3. So I'm going to put the root of 3 here. So our side lengths are 1, 2, and the root of 3. So now, what are these angles in here? Now that we know the side lengths, let's go back to this equilateral triangle. What do all the angles in the equilateral triangle have to equal? So let's just erase this altitude. Before we even had this guy here, what did each of these angles have to be? Well, if it's an equilateral triangle, that means that all the angles are equal. So this had to be 180 divided by 3. Each of these had to be 60 degrees. So this was 60, this was 60, and this is 60. Now remember, we took an altitude and we brought this down. So what angle has to exist down here? What angle is this? Oh, it's 60 degrees. So I'm going to put 60 degrees here. What is this angle right here? Well, because it's equilateral triangle, when I dropped an altitude down, it's going to cut this angle exactly in half. So that means that this angle that's left over just from here to here must be 30 degrees. So we can add also that this is 30 degrees. So now taking a look at this triangle, we can find the sine, cos, and tan of 60 degrees and 30 degrees because we have each of these sides of a right angle triangle that has 60 and 30 degrees in it. So for example, if I wanted to find sine of 60, let's just add it in here. If I want to find sine of 60, I would just take the opposite side over the hypotenuse side. It's just root 3 over 2. So I'm going to fill that in. The sine of 60 is just root 3 over 2. What about the cos of 60? The cos of 60 would be adjacent over hypotenuse. So it would just be 1 over 2. So I'm going to add that in, 1 over 2. What about the sine of 30? Well, if here's our 30 degrees, here is our opposite, and here's hypotenuse. So our sine would be opposite over hypotenuse, 1 over 2. And our cos of 30, our cos of 30 would just be adjacent over hypotenuse, so root 3 over 2. Root 3 over 2. So we just derived the exact ratios of the sine and cos of 30, and as well as the sine and cos of 60. We could also do the same thing for tan. Let's try to do the same thing for 45 now. So we're going to start off with an entirely different shape. We're going to start off with a, we're going to start off with a square with side length 1. So let's label this. So this is a square with side length 1. We are going to write this is 1, this is 1, this is 1, this is 1. And now it says split the square into 2 triangles and solve the triangle. So split the square into 2 triangles. So here we go. We'll draw a diagonal all the way across. Here are our 2 triangles. What angles do we have? So let's start filling in our triangle down here. So let's do the side lengths first, and then we'll deal with the angles. So just taking a look at this guy right here is duplicated right over here. We know these side lengths, those are 1. So I'm going to write in a 1 and a 1. So this length is 1, this length is 1. Let's find this length. Really quickly, we can just use the Pythagorean Theorem. So we know that 1 squared plus 1 squared has to equal that c squared. So our c squared has to equal 2, which means that our c has to equal the square root of 2. So we know this length right here is the square root of 2. Now let's try to figure out the angles. Let's go back to the square to figure out our angles. We know that originally this used to be, each corner was 90 degrees. And because it's a square, when we took a diagonal across from each corner to each corner, this is going to exactly split into half, which means that this angle is now 45 degrees. Same with this angle right over here. So let's fill in what we do know about this triangle here, which is that these angles up here are 45 degrees. So we have all the side lengths of a triangle with our right angle triangle with 45 degrees. So now we can derive what the sine, cos, and tan of 45 degrees is exactly, just like what we did for the angles of 30 degrees and 60 degrees. So what is the sine of 45? The sine of 45 has to be opposite over hypotenuse. It is going to be the same for both of these 45s. So the sine of this 45 is 1 over root 2, opposite over hypotenuse. Sine of this 45 is also 1 over root 2. So the sine of 45 is just 1 over root 2. And let's do the same thing for cos. Cos of 45 is just adjacent over hypotenuse. So again, 1 over root 2. Same with this 45, 1 over root 2. So the sine and the cos of 45 degrees is exactly the same. And that's because it's coming from an isosceles triangle, 45 degrees. Okay, so here are our ratios that we need to remember. We can always remember them by deriving these triangles. There's actually another graphic organizer we're going to use called the unit circle to help us remember them, but we need to remember these ratios. Tan isn't on here, or tan isn't in our chart. We are going to derive tan as well. So what we're going to do is on the next page, we're going to summarize all of our ratios that we have found into a table. So here's our table. Let's fill in what we do know. So we know what the sine and cos of 60, 45, 30, 45, and 60 are. So let's fill it in. Back on the previous page, we derived that the sine of 30 is 1 over 2, and that the cos of 30 was root 3 over 2. Then we found that the sine of 45 was 1 over root 2, and the cos was exactly the same because it came from that isosceles triangle. And then once we have the sine and cos of 30, we can remember the sine and cos of 60 as well because it came from the same triangles, so these two are just switched. So the sine of 60 is just root 3 over 2, and the cos of 60 is just 1 over 2. All right, so these are the only ones I really remember. Everything else can be derived from these ones, even tan. So there's a sneaky way that we can come up with tan, and it's derived from this identity, that tan of an angle is equal to sine over cos of that same angle. We can prove that this is true by quickly writing out what exactly sine is and what cos is. So sine we know is just opposite over hypotenuse. So I'm going to write, let's just prove that this is true. So sine is equal to, so I'm going to do sine of theta over cos of theta is equal to, sine of theta is opposite over hypotenuse, and cos of theta we know is adjacent over hypotenuse. So how is this tan? Well, let's simplify this. We know that we have two fractions dividing, so we have opposite over hypotenuse divided by adjacent over hypotenuse. So we can just flip this and multiply. So this is going to be opposite over hypotenuse times the reciprocal of a over h, which is h over a. And then look, these h's are going to cancel out, and we're left with opposite over adjacent. So that means that the sine over the cos ratio of the same angle is just equal to the opposite side over the adjacent side. Isn't that just tan? That's just equal to tan. So sine over cos is just equal to tan. So that's a really important property we're going to use over and over and over again. So we're going to use it for this table. Instead of deriving what tan is from the special triangle, which we absolutely can, we can instead just take sine over cos. And if we divide 1 over 2 divided by root 3 over 2, we're going to get 1 over root 3. If we take the sine over cos of 45, we have 1 over root 2 divided by 1 over root 2. That's just the same thing divided by itself. So it's just going to be 1. And if we take root 3 over 2 divided by 1 over root 2, we're going to flip this and multiply. We're just going to get root 3 over 1, or just root 3. So I don't need to memorize tan, because if I know sine and cos, then I can come up with tan by just using this property here. Cosecant, secant, cotant, also very easy. We know cosecant is just the reciprocal of sine. So if sine of 30 is 1 over 2, cosecant must be 2 over 1, or just 2. Let's do it for 45 now. It's just going to be the reciprocal of sine, so it's going to be root 2. And then the reciprocal of sine of 60 is going to be 2 over root 3. So finish the rest of the chart on your own, check back in the video, make sure you got the right answer, but come up with the secant and cotant of these angles as well. Alright, so triple check your answers. Remember, secant is just 1 over cos, the reciprocal of cos. So it's related to all these values here. Cotant just 1 over tan. So there is actually, if you're looking at this chart saying, how the heck am I ever going to memorize this? Remember, we're actually only going to remember these values. You really only need to remember 3 values, and the rest of them we know where they're derived from. We can just figure them out. And we are going to put them in a graphic organizer called the unit circle. But let's just do some practice now with them. So using the chart, we haven't gotten to the point that we can actually memorize these yet, so not a problem. So we're going to use the chart when we need it. And let's start filling out these. So this is determine the exact value of each trig expression. So we'll do one slowly together, and the rest of them I want you to try on your own and just check what the solutions are. So let's start with this first guy here. So it says we got to find an exact value. So what we're not doing is plugging this into the calculator. We are not doing that. We're going to derive the exact value by using our ratios that we have here. So this is the sine of 45 times the cos of 45 plus sine of 30 times sine of 60. So let's fill in what we know. These are all special angles. So we have the exact trig ratios. We have the exact trig ratios for 45, 60, and 30. So the sine of 45, just using our chart up there, is just 1 over root 2. So I'm going to change sine of 45 to 1 over root 2. The cos of 45 is also 1 over root 2. And then we have plus the sine of 30. The sine of 30 is just 1 over 2. And the sine of 60 is root 3 over 2. Okay, let's not leave it like this. Let's simplify it as much as possible. So bedmass, we got to multiply first. So I'll multiply these fractions. 1 times 1 is going to be 1. Root 2 times root 2 is going to be root of 4, which is just going to be 2. If you need to do it in 2 steps, do it in 2 steps. If we can just go fast, root 2 times root 2 is just 2. Next one, we got plus 1 times root 3 is just root 3, so plus root 3. And 2 times 2 is 4. Let's again not leave it like this. Let's combine these fractions. So I'm going to multiply this guy by 2. So we have on the top, we've got 2 plus root 3 all over 4. And that is as simplified as we can possibly get it. So if we really wanted to, if we had access to a calculator, we could check really quickly if we have a correct answer by actually putting this in the calculator, pressing equals, and then checking what 2 plus root 3 all over 4 is. It should be exactly the same. This is just the exact answer. So try the same thing for B and C and check back in the video just to make sure that you've got the right answer. Go for it. Okay, so let's quickly check our answers. So here are the answers you should have gotten for each of them. Let's just go over this guy. 1, we have 1, minus tan of 45 is just 1, times the sine of 30, that's a half. We know 1 minus 1 is going to be 0, so whatever this is going to be 0 anyway. So this is what really matters here. We have a negative 2
times sine of 45, that's just 1 over root 2. So negative 2 times 1 is negative 2, all over root 2. This guy's going to be 0, so we have 0 minus 2 root 2. Negative 2 root 2 is our final answer. Let's take a look at this guy here. Cotan 45 is 1, cosecant of 45 is root 2, secant of 30 is 2 over root 3, cosecant of 60 is 2 over root 3. This is easy. 1 times root 2 is root 2. This guy is going to be 2 times 2 is 4. Root 3 times root 3 is going to be root 9. The square root or positive square root of root 9 is 3. So root 3 times root 3 is just going to be 3. We can finish the rest of this guy off by just making like denominators. So we have, put this over 1, and I can multiply both of these by 3. So at the top here I have 3 times root 2, there it is, plus 4. We can't combine those, they're not like terms, so just all over 3 and we're done.